Thank you for giving me this opportunity. I'm sorry I could not present there in person. So I will be talking about the low resolution spectroscopic view of the tidal disruption events. So this work is being conducted with the data taken from SALT and two other telescopes like HCT and SDSS and some other telescopes. So in general, when we are talking about the extreme transients can, in general, can happen at any position of the galaxy. In the right hand side of this slide, you can see a schematic picture of a galaxy, where the red points have been shown as a probable location of the transit. But if you look towards the more central part of of a galaxy, within 100 parsecs, there may be many things like AGN variability, changing locations, micro lensing, nuclear supernova, tidal disruption event, and many other unknown phenomena. Now, when these things are happening at a distance of several megaparsec, so often we will not be able to distinguish it spatially from the center, and essentially it will be important to understand its physical signatures, so like the light curves, spectrum, and all those. And this sometimes makes the transients, detection of the transients, and to understand the nature much more complicated rather than when it is happening at the center of the galaxy. If it is not happening at the center of the galaxy, then it will be relatively easier. And if it is happening to the center of the galaxy, it will be relatively complicated. If I pick up the one of the such transients, which are tidal disruption events, so these are the tidal disruption of stars. So when stars falls very near to the center of the black hole, central supermassive black hole, some part of the stars gets disrupted and some part gets fan out, and in this process, a huge eruptions basically is a kind of explosions happens, and this outward propagating material produce different emissions in different wavelengths, particularly in UV and optical, but also in IR and occasionally in X-ray and radio if it interacts with the surrounding materials. Now, this one of the principal characteristics of the tidal disruption events, its mass infall rate, which follows the luminosity, goes at e⁻⁵, which is some sort of hallmark for the tidal disruption process. Now, if we look at, there are different kind of tidal disruption events. Now, when with the increasing survey facilities, we have seen that the tidal disruption events may be with lower luminosity, maybe higher luminosity. There may be a slow rise, there may be a sharp rise. So it's essentially asked for whether their progenitors or the systems are similar or not. We have also found, for example, here is one case where we have shown that this particular system, this 2020 OHL, or here it is shown by the black dots. So these are, although it looks like a tidal disruption events, but it is not a tidal disruption events. We have shown by the multi-wavelength observations using the data from Chandra and VLA. We have shown that this object is basically a fluctuation in a very low mass, in a very low luminosity radio galaxies. So all of them which are initially classified as tidal disruption event may not be a tidal disruption. So this makes the life much more complicated. Actually, if you look at the theoretical prediction rate of the tidal disruption events, so it is of the order of 10⁻⁴ per galaxy per year per MPC cube. But the observed rate is much lower, which is of the order of 10⁻⁴ to 10⁻⁵, about one order lower. So the things did not change much between IPTF and ZTF surveys, and actually we have seen that getting the TDEs among all surveys is about, as you can see here, 1.4%. So what are the constraints which are behind the low value of the measured TDE rate is one of the basic questions in the field of TDEs. Is there also any dependencies of the TDE rate on the environment and the galaxy type? This is also one of the queries. And is there observational biases, and how does it create the complexity and the TDE science? Are there some of the basic questions in the TDE field? One of the things I want to show here that in any cases, with this galaxy evolution, if you look, there is one side, there is a star formation phase, one is another side is the AGN dominated phase, but there may be two possibility of this evolution. One, in one channel, it may be through a less dusty medium, and in other channel, there may be very dusty medium, which is basically the AGN will be buried inside the very dusty medium. So in such cases, in most of the cases, when we are looking at the TDEs or other nuclear transients, we mostly classify it with the high UV dominated, and most of the time we actually first observed in optical, and then we detect it in UV and other wavelength. So remember, if something is happening in the below channel, this channel 2, then probably we will not be able to detect many of them. So actually there will be a large fraction of the TDEs or nuclear transients will not be detected if it is going through this path. So there is a possibility that since it's the BRICS summit, I would like to bring one attention that we are doing the survey science in optical. There is a possibility of doing the survey science in IR, basically near IR, which may able to detect the transients happening in those medium where it is very dusty. It is embedded in a very dusty medium. It was very precisely shown by Seppo Matela in 2018, where he has shown that there is a TDEs in an ARP galaxies, and it was never observed in optical or UV, but it was found in IR, and later it was found in radio as well. So there is a scope for the IR survey, and which will give us more new kind of transients which are happening within the very dusty and obscure medium. If you look at if you talk about the host of the tidal disruption events, there is a lot of work was done by French and Weber. So they have shown that the mass of the tidal disruption galaxies, which are hosting the tidal disruption even galaxies, so those galaxies are relatively less massive in comparison to the other galaxies, and also their stellar mass and the star formation rate are also quite different from the other normal galaxies where the tidal disruption events are not occurring. The similar things also shown, not exactly similar, but shown that the TDEs are quite different. So the galaxies which are producing TDEs or TDE-like events are quite different from the AGNs. Using the Wise color diagram, it was shown already. So what we have done, we have actually taken as much as data we can get from of our TDE host. We have used basically the spectrum from different telescopes, from HCT, from SALT, NORT, and other survey telescopes, and we have tried to increase the sample size as much as possible. So we have seen that this the TDEs, the host galaxies of the TDEs are relatively quite bright and is around -17 mag in G band. It's absolute magnitude. And one more thing we found that if you look if you compare with this plot, you will see that so this is the red curve shows the highest luminous observed intrinsically luminous transient observed by ZTF, and this is the lowest intrinsically low luminous TDEs observed by ZTF. So there is the typical survey detection limit. So you can see that there is some cutoff where 0.1 around redshift, within which if we do the volumetric search, then we can find out that whether what is the difference between the host galaxy type of low luminous TDEs and the high luminous TDEs. And it's in fact this all low luminous TDEs detected by ZTFs are within this range. So this paper is almost is in preparation. So I am showing some of the early results. So what we have done, we have actually It is done by one of my MSc student, who is working in this particular project for last 1 year. So some of the early results are as follows. So we have actually segregate the galaxy component and the stellar component using the code PPXF, and we actually analyze these two components separately for TDE for these galaxies. But we found that if we look at the absorption lines only, then we found that there are two different kind of hosts I have shown. One of these are the absorption lines in those hosts where there was no emission lines. So essentially, these are the absorption dominated spectrum, and sorry, other way. This is the host where there are the emission lines, and these are the hosts where there were no emission lines initially. So what we have found that the absorption, this spectral features, the stellar features are not very much different. But what we have found that the equivalent width of these lines in those hosts which has no emission line, so essentially the absorption dominated hosts are much more than the hosts where there are emission lines. So it essentially shows that these are those galaxies where early the star formation happened, but now the star formation has been quenched. So these are basically post-starburst galaxies, and these are relatively new galaxies. So there are different kind of galaxies. Mainly these are the two type of different galaxies, and we further actually seen the black hole mass distribution of these galaxies. So these blue are shown that the host galaxies were all the TDEs, and these are the red part, and there are only few objects found where we have the low luminous TDEs. So it has been shown that the low luminous TDEs and in general TDEs black hole mass, SMBH mass are relatively less in comparison to other. So one of the things that this TDE may be a good tool to find out the intermediate mass black holes, and but there is also a problem in understanding that which object is TDE and whether it is a TDE or not. So that is one problem, but essentially TDE is one of the tools which can find out the intermediate mass black holes. Further, with the emission line galaxies, we have performed the PPT diagram, and we have found that this actually if we divided all our samples in different galaxies, we can find out that these events are happening most of the time in those systems where these are the most absorption features are there. And I mean, basically there is no emission line, so basically absorption dominated system, and in other galaxies it is relatively less, and we are basically working on this. Most likely there is a geometry effect which are showing which shows that these are much more which are showing that these galaxies are much more TD prone in compared to other galaxies which have either star forming galaxies or AGN type galaxies. So basically, the take-home message is the nuclear transients are very rare. The rate of TDs and the measured and this rate of this measured rate may be influenced by the environment and the geometry of the system. One of the things is near sky survey may be important to find out the nuclear transients which are hosted inside the highly obscured medium, and the masses of the SMBHs are very the masses of the SMBHs or the potential TDE candidates are relatively less in comparison to the mass of the SMBHs in other galaxies. Essentially, TDE may be a potential tool to search for the intermediate mass black holes. And of course, there are other different nuclear transients, like one I showed, 2020 OHL, and apart from that, there are association 15 LH and others. So which showed sometimes some signatures which are not exactly TDE, or this is the signatures of supernovas are also there. So multi-wavelength observations and high precision astrometries are required to do this to understand the nature of such system. And maybe in the BRICS collaboration we can do systematic observations of such nuclear transients to find out their origins and their origins. Yeah, thank you.